This is the 16th video and the first video on shear stress and strain. In this video, the topics covered are shear stress and shear strain, modulus of rigidity, complementary shear stress, single and double shear stress, punching shear, and few problems on shear. Shear stress. Here, this is a block A, B, C, D as shown in figure. At AD, it is fixed. Now, if a force P is acting parallel to the plane BC like this, and under the action of this force, if the body is in equilibrium and it doesn't move from its place, it is at rest, it doesn't happen that due to this force which is acting in the positive x direction, the body starts moving in the positive x direction. It just means at AD here at the bottom, equal and opposite force is developed, and that is a reactive force which is equal to P. Then only this body ABCD will be at rest. Now if I consider a section XX here, cut it into two parts. One is the upper part and two is the lower part. Now if I draw the free body diagram of the part 1, then this is the section line here XX that's shown, this is BC, and this is the force P which is acting here. Now if ABCD is in equilibrium, it's each and every part is also in equilibrium, that is at rest. So when this force P is acting here in the positive x direction, that means at section XX a reactive force must act here as shown in the negative x direction. Then only this part 1 will be in equilibrium. So this is the free body diagram for part 1. Now if I draw a free body diagram for the part 2, then this is the force P, reactive force P, which is acting here in the negative x direction, and here at the top XX a reactive force R will be developed in the positive x direction. Then only this block AD, which is the block 2, will be in equilibrium. So for equilibrium, R must be equal to P. So the intensity of shear resistance along the axis XX is called as shear stress. Here shear stress is equal to shear resistance divided by the shear area. R is the shear resistance and A is the shear area. Now R is equal to P, so this P is called as shear force and shear area is A. So P upon A. Now which is the area which we consider? Now this is the, if I consider section XX, then we will consider this length into the dimension which will be perpendicular to the screen, which we can't see. So or here it is BC into the thickness which we can't see here of the block ABCD. So this is the BC plane. So that is the area under shear. So P divided by A, which is the area under shear. The symbol for shear stress is sometimes used as small q or it is tau. So this is how a shear stress comes into play. Now let us see what is a shear strain. Now suppose this is the block again A, B, C, D, where the force P is acting on the plane BC. A reactive force P is developed at AD here at the bottom. Now bottom AD is fixed, so points A and D will not move. But suppose due to this shear force P, the B shifts to B dash and C shifts to C dash as I have shown here. So the distortion of block A, B, C, D to A, B dash, C dash, D under the action of two forces P as shown in figure. These are the two forces P which I have shown. So what happens is B shifts to B dash, then there will be a angular deformation phi. So the angular deformation phi will be equal to B dash, that is this B dash, or C dash divided by L. L is this length AB. So shear strain, which I am writing it as epsilon, SH stands for shear, will be equal to tan phi, that is this tan phi, and this tan phi is so small that it can be taken equal to phi, and this phi will be B dash divided by AB. So B dash divided by AB is tan phi. We can very easily see here tan is this side B dash divided by the adjacent side AB, front side divided by the adjacent side. So it is displacement of width. This is the BC is the width. So this is the displacement of the width divided by original height of the block, that is L. So displacement of width divided by original height of the block, that is a shear strain. Now the modulus of rigidity, a ratio of shear stress to shear strain, is called as modulus of rigidity. Just like ratio of direct stress to direct strain is called as modulus of elasticity, similarly ratio of shear stress to shear strain is called as modulus of rigidity. It is denoted by capital G, capital N, or capital C. We will use the symbol capital G for modulus of rigidity. So modulus of rigidity is shear stress divided by shear strain. So G is equal to, I am representing shear stress as tau and shear strain as epsilon SH. So these are the basic things in shear. Now here, what is a very important thing to understand is, suppose this is a block. Just like this is block A, B, C, D. So A here, B here, C and D. So on this plane, if the force acts perpendicular to the plane, it is compressive. If it is compressive, then compressive stress is developed. If it is a pulling force, then the tensile stress is developed, and that we call it as a direct stress. Here, when the compressive or tensile stress is developed, the force is perpendicular to this plane, and when a shear stress is developed, at that time the force here is parallel to the plane. That is the main difference between the shear stress and compressive stress or tensile stress. So now, till now we have seen only two types, compressive stress and tensile stress. Now we are learning a third type of a stress, that is a shear stress. And in the shear stress, the area under shear, the plane, this area is parallel to the shear force. Whereas when it is compressive or tensile, the area is same. This is the area, but the force acts perpendicular to the plane. That is the main difference. So in shear, the force P acts tangential or parallel to the plane. Here the plane is BC. This force P acts perpendicular to the plane BC or the cross-sectional area for direct stress sigma. Now again, let us consider the same block A, B, C, D. This is the distorted position B to B dash and C to C dash. Now what is important here is, point C has shifted to C dash. So the diagonal AC was the original dimension. After distortion, the diagonal becomes AC dash. Now here you can very easily observe that AC dash is greater than AC. Here you can observe AC dash is greater than AC. The length AC dash is more than the length AC. So there is increase in length of AC to AC dash. So the tensile strain is induced along the diagonal AC. So here I am showing the forces, tensile forces along AC. In the direction of AC, I am showing the pulling forces. So the diagonal tension is there for AC. Similarly, now let us consider the diagonal BD. The diagonal BD has changed to B dash D. So here we can very easily observe that B dash D is smaller than BD. It just means the length of the BD has reduced to B dash D. There is reduction in length, means compressive strain is induced along the diagonal BD. So here, parallel to BD, I am showing these compressive forces. So diagonal compression for BD. So for the diagonal BD, compressive strain is developed, and for the diagonal AC, tensile strain is developed. Now let us try to understand what is a complementary shear stress. Now this is the figure here. This is the block A, B, C and D. Now consider this is a cube of side A with face area A square. Consider the face ABCD as shown in the figure. Let the shear stress tau be acting on top and bottom faces of the cube. Now if at the top face the shear stress tau is acting in the positive x direction, then for this block to be in equilibrium, here at CD the tau will act in the negative x direction. So these two shear stresses, they balance each other and the block is in equilibrium. Now the shear force acting on top and bottom faces of the cube will be, now tau is the shear stress. If I multiply with the area will be, it is a cube, so area is a square. So if I do tau into a square, then I get the shear force acting at on the face AB and CD, tau into a square. Force in stress into area will give me the force, so shear force will be tau a square. Now these two parallel unlike forces constitute a couple of clockwise moment. Clockwise means turning in the direction as the needle of the clock moves. So 12, 1, 2, suppose this is 12, then 1, 2, 3 like this. So this direction is called clockwise. So now this tau a square will be the force here, tau into a square will be the force here, and these two forces, they will form a clockwise couple. So due to these two forces, if this ABCD block turns, it will turn in the clockwise direction, and the moment will be, now distance between these two is again a because it's a cube, so tau a square into a, that is tau a cube, is the couple, and this couple is known as induced couple, and it will give a clockwise moment. Now for equilibrium of this induced couple, another couple formed by the forces due to shear stresses, that is tau dash, on two vertical faces AD and BC. The moment of this balancing couple will be tau dash into a square into a, which is equal to tau dash a cube. This balancing couple is known as resisting couple, and it is anti-clockwise. Now anti-clockwise is exactly opposite to clockwise. This is the direction of anti-clockwise. Now here I have shown on, if the two shear stresses tau are acting on plane AB and CD giving a clockwise couple, and still if the body is in equilibrium, then there must be two shear stresses which are developed on the other two faces. Now on BC and AD, on these two faces, the shear stress developed is tau dash. Now shear force due to tau dash will be tau dash into a square, and couple will be into a, that is tau dash a cube. And if this tau dash a cube and tau a cube, if they are equal and opposite, then only ABCD will be in equilibrium. So for equilibrium, the moment of induced couple must be equal to moment of balancing couple. Induced couple is tau a cube and balancing couple is tau dash a cube. If a cube gets cancelled, so this tau must be equal to tau dash. This pair of shear stresses tau dash on two vertical faces AD and BC are known as complementary shear stresses. This block is said to be in a state of simple or pure shear. So just like sometimes when we go to the market, they say that buy one get one free. So if you buy one, another comes automatically as a complementary with that. Same way, if the tau shear stress is, pair of shear stress is developed on two faces and it is giving a clockwise couple, then and if the block is in equilibrium, then for equilibrium, automatically on the other two faces, anti-clockwise couple is developed, and a shear stress is developed on these two faces, which is equal to tau dash, where it is equal to tau. and the pair of shear stresses tau acting on two parallel faces is always accompanied by a pair of complementary shear stresses tau dash on two parallel faces perpendicular to former faces, and this is known as complementary shear stress principle. So this tau dash pair of shear stresses, it is developed automatically, then only, and if it is developed, then only the body will be in equilibrium. Here what is important to understand, if this tau, when it is acting on the face AB, if it is shown from A to B, then this tau dash must be shown from C to B. So the arrow must be, if it is this tau is arrow is towards B, the tau dash arrow also must be towards B. Here the arrow of tau is towards D, so the arrow of tau dash must be towards D. It should not happen that tau arrow is towards D and here when I show the tau dash, the arrow is pointing towards A. If the arrow here, tau dash arrow starts at A, I show it at A, and for this tau dash, if I show the arrow not at B but at C downward, then this pair will become clockwise, it will not become anti-clockwise. That is very important, that when we draw this figure, the arrow here, these two arrows are at D and here these two arrows are at pointing B. It must be at the same point. Or if I show one arrow at B, another arrow at C, another arrow at D and another arrow at A, then this whole thing will become a clockwise and they will not balance each other. The tau dash must give a anti-clockwise balancing couple. That is something important. Now here we are going to study single shear and double shear. Now if these are the two plates which are connected by a rivet here, and a tensile force P is acting on these two plates, and these two plates are connected by this rivet. If this P goes on increasing, then what happens? This, due to this force P, this rivet fails and this bottom plate will move towards right and the top plate will move towards the left in this direction, and this rivet, it breaks into two pieces, and the upper part of the rivet will be in the upper plate and the lower part of the rivet will be in the lower plate. Here I am showing only the rivet how it fails. So this is the upper part of the rivet, and here this force is acting like this, so it will be here, and this force is acting towards right, so this is the force which is acting towards right, and this is the lower part of the rivet. So this rivet gets cut here in this plane. So this is the plane, shearing plane, where the rivet gets cut, and here if the diameter of the rivet is D, then pi by 4 d square is the area under shear, and you will see here that the shear force is acting here parallel to this cutting plane. This is the force which is acting parallel to this cutting plane, and in single shear there is only one shear plane and the rivet breaks into two pieces and there are two plates. Now if instead of two there are three plates like this and they are connected by a rivet, now here on the top and the bottom plate the force P is acting. In the middle plate the force is 2P. So this 2P and P, they balance each other. Now if the P increases and there is a failure, and if this middle plate it moves towards right, and this rivet now breaks, now here it will break into three pieces, and there will be one part in the top plate, one part in the middle plate, and the third part in the lower plate. So here you can very easily see this is the top part, this is the middle part, this is the lower part, and here the rivet has failed into three pieces. Now these two forces P that I am showing here, this is the force P and here it is 2P. This will, one will act at the top here and another will act at the bottom here. So this is the shearing plane. One failure is here and this is another. So one shearing plane here between top and the middle, Another shearing plane is here between middle and the bottom. So at two planes the rivet breaks here. So here area under shear is double. Now in for a single shear stress it will be P, this force P divided by pi by 4 d square. That is the shear stress. P is the shear force and area under shear is pi by 4 d square, where d is the diameter of the rivet and P is the shear force. For the double shear stress, now the force is 2P divided by bracket open. Here we have to remember we must take the area double because there are two planes. One plane is here and another plane is here. So 2 into pi by 4 into d square. This is the area under shear, where d is the diameter of the rivet and 2p is the shear force. Usually when we see that the breaking stress is same, if in the single shear if the breaking stress is 50, in double shear also the breaking stress will be 50 only, but the force which is taken is increases and it becomes 2p, and the area also is doubled, so the stress remains the same. Now let us come to punching shear. Now here what is, this is a plate. This is a plate and we want to make a say circular hole in this plate. So what we do is we take a circular rod. Suppose I want to make a hole of 10 mm diameter. Then I take a circular rod of 10 mm. One face is plain here and another face is this like this V shape and it is sharpened edge, and that is called a punch. What we do is, if we hold this punch with our left hand and with the right hand a man will put this punch on the surface of the plate where he wants to make a hole, and with the hammer in the right hand he will apply a force F like this on the punch, and when he hits the punch with the hammer, this punch enters the plate and the plate here will break and this piece of the plate will move down, and that is how a hole is punched in the plate. Now when the force is applied to the punch, this is the force and this is the surface area. So what happens is the force for the punch is a compressive force. So the compressive force F in the punch will be equal to the compressive stress sigma of the punch into A, area of the punch. Now the sigma of punch, and what is the area? Suppose this cross section is a circle. The cross-sectional area of a punch is a circle, then the area is pi by 4 d square, where d is the diameter of the punch, and most of the time we want the circular holes in the plate, so we use the punch to make the holes, and the diameter of the whatever is the diameter of the punch, the same will be the diameter of the hole. Now when this piece is get cut here, then the force which is acting on the plate, now in it has sheared here this surface and this surface, so this is the surface which has cut and the force is acting parallel to this surface. So the force F is compressive for punch, but it's a shear force for the plate. And what is the area under shear for the plate? So for the shear force in the plate, it will be equal to tau, that is the shear stress of the plate, into thickness of the plate. Now this is the thickness of the plate and this is parallel to the thickness, the force is acting parallel to this thickness, so tau of the plate into, now area under shear will be thickness of the plate into circumference of the hole. Now here I am showing that this is the plate and this is the circular area which is cut. Now this is the part. Now if this circular shape is made straight, it becomes something like this, and if you make it full stressed, then what is the length? So this length is pi d, that is the circumference of the hole, into this thickness t. This is the area under shear, pi d into t. So T, thickness of the plate, into circumference of the hole, that is the area, and into shear stress of the plate, that gives us the shear force in the plate. Now this force, compressive force in the punch is equal to the shear force in the plate. So this, because the same force which is in the punch is getting transferred to the plate. So compressive force F in the punch is equal to shear force in the plate. Now this compressive force is equal to sigma punch into area of punch is equal to shear stress of tau of the plate into thickness of the plate into circumference of the hole. Now if I substitute the value, it is sigma into area of punch is pi by 4 d square, tau is the shear stress of the plate into this is the thickness of the plate, and circumference of the hole is pi d. Now this pi d from here and this pi d here, they get cancelled, and if I write d is equal to, then here t in tau into t is what remains, tau into t, pi d gets cancelled. Here pi and 1d gets cancelled, and 4 when I take it on this side it becomes into 4, and sigma when I take it on this side it becomes divided by sigma. So the formula becomes diameter d is equal to tau of the plate into thickness of the plate into 4 divided by the sigma of the punch, compressive stress of the punch, that will give me the diameter. So sometimes when we want to find out the diameter, we will use this formula. Now punching shear, a hole is punched in a steel plate having thickness T due to shear force acting tangentially to the area of circumference of the hole. So this is the punching shear. Now if we want a rectangular hole, then the punch size is b into d, that is the shape of the punch is not circular, then it will be of the size b into d. So this is how we punch a rectangular hole, and this is b, this is d, and this is the thickness t. Now here this is, if I want a perimeter, now this rectangle is the perimeter, so perimeter will be b plus d plus b plus d. So this is b here, again this is b on this side, d here and d here. So the perimeter will be this d plus b, again this b and d. This is the straight length which is getting cut, and this is the thickness. So shear area will be 2 into bracket b into b plus d into t, and the circumference for the rectangles, for circle the circumference is pi d. If it's a rectangle, then the circumference will be 2 into bracket b plus d. So if I take this will become twice b plus twice d. If I take out 2 common, it will be 2 in bracket b plus d. This is the circumference. If I multiply with the thickness t, that gives me the shear area if the punch is rectangular. Be a master. Thank you.